So in this last part of the lesson, we're going to look at slope again. But now we're going to look at slope when we have data given in tables. So the first thing I'll talk about is computing rise over run given a table of data. And then we're going to just look at tables and decide whether or not the table represents a linear relationship. And finally, we'll talk about generating a table of data from a verbal description. So what does rise over run look like in a table of data? Well, let's look at a table. Here's a table of solutions to the linear equation y equals 5x plus 3. Now, one of the first things we notice in this table is that we can see a pattern. We can see that the x values are increasing by 2 as we move from one row of the table to the next. The y values are increasing by 10. So it looks like we have a run of 2 and a rise of 10. I'm just going to use the formula we have for calculating slope. And if I choose the first 2 points in my table and calculate the slope, I end up with that rise of 10 over the run of 2 over a slope of 5. And I'm going to get the same rise over run regardless of which pair of points I look at. So taking the second 2 points, I get a rise of 10 over a run of 2 for a slope of 5. Next pair of points gives me a rise of 10 over a run of 2 or a slope of 5. This happens regardless of the pair of points I choose. Now this is just some of the solutions to this linear equation. Here's another set of solutions. In this case, my x values are increasing by 1. My y values are increasing by 5. So it looks like I have a rise of 5 over a run of 1. Let's perform some slope calculations. So using our same formula again, looking at the first pair of points, I have the slope is -2 minus -7 over -1 minus -2. That gives me 5 over 1, or 5. Looking at just some other pair of points in the table, again, 13 minus 8, that gives me the rise of 5 over 2 minus 1. That gives me the run of 1. Again, I find a slope of 5. Now, sometimes when we're looking to solutions to an equation, as we are in this situation, there may not be such a nice pattern. If we look at the x values here, we see that the x values increase by 4, by 3, by 3, by 4, by 8. So we don't have a consistent change in the independent variable, x. But when I calculate slope, choosing pairs of points, when I look at the first pair of points, I get a rise of 20 over a run of 4. That reduces to 5. The next pair, I get a rise of 15 over a run of 3. That reduces to 5. Same thing from the next pair. Now in this pair, I get a rise of 20 over a run of 4, which is 5. The last pair, I'm getting a rise of 40 over a run of 8, which again is 5. Now, I don't have to look at consecutive rows in my table. When I choose the first row and the next to last row, I end up getting a rise of 70 over a run of 14. 70 over 14 reduces to 5. I could even go the other way. I could look at going from 103 down to 28. That's a rise of -75 over 20 down to 5. That's a run of -15. The rise over run once again gives me 5. So no matter how I look at it, the slope between any two pairs of points, which are solutions to this equation, is going to be 5. And we have a 5 right here in the equation. So slope We can use our formula to evaluate slope. And another way we can think about slope is that it's the change in the dependent variable over the change in the independent variable. We don't always use x's and y's. And then finally, we can just think about slope as rise over run. So earlier in this lesson, we noticed that lines have constant slope, and that the slope between any 2 points on a non-vertical line is the same regardless of what 2 points you pick. Well, we just saw the same thing in our table. And in our table, we just had solutions to a linear equation, and solutions to a linear equation in 2 variables exhibit this constant slope. So if I choose any 2 solutions, I'll get the same slope regardless of which 2 solutions I pick. So let's look at this whole thing of rise over run again with a table. I have a table of solutions to the equation v equals 80 minus 10t. So when a table of data is given in 2 rows, the first row typically represents the independent variable. So t will be my independent variable, v my dependent variable. So I want to find the slope of this equation using the data in my table. So when I look at rise over run, what's happening to the v values? As I move from one column to the next, the value of v is decreasing by 20. The value of t, the independent variable, is increasing by 2. So when I compute rise over run, in this case, my rise is -20, and my run is +2, so I calculate a slope of -10. Notice the constant -10 is right in my linear equation. So now I have the same table of data, but now I've labeled the variables. Now we're being told that t represents time in seconds, and v represents speed in kilometers per hour. So given that v represents the speed of a car in kilometers per hour, t seconds after the brakes are applied, state the practical significance of the slope. So now when I write down my slope, I'm going to consider units. So I had my rise was -20, but now I know that's measured in kilometers per hour, and my run is 2 seconds. So my slope is -10 kilometers per hour per second. So what does this mean? This means that the speed of the car decreases at a rate of 10 kilometers per hour per second after the brakes are applied. So in the context of the problem, the slope has a practical significance. So we talked about this in an earlier part of the lesson as well. Slope can always be thought of as a rate of change. So we might have something that's increasing, and we would say that the dependent quantity increases at a rate of the slope, whatever it happens to be. When we were looking at the speed of the car in this last example, it was the dependent quantity decreasing at a rate of slope. And remember, we need to think about the absolute value of slope. So in the example we just looked at, the speed of the car decreases at a rate of 10 kilometers per hour per second. So now let's talk about whether or not a table of data describes a linear relationship. So this is just a review of something we talked about earlier. Solutions to a linear equation in 2 variables exhibit a constant slope. And this is true regardless of what 2 solutions we pick. So when we're looking at a table of data, we want to think about slope. So does the data in this table 3 suggest a linear relationship? Well, let's see if we can figure out the rise over run by looking at the table. So if I look at my run, my x values are increasing by 3 as I move from one column of the table to the next. My y values are decreasing by 25. So looking at the table, we see that the rise is negative 25 and the run is positive 3. So our slope, rise over run, is going to be negative 25 over positive 3. So yes, the data in this table represent a linear relationship. Since the slope is constant. Let's look at another example. So here we have another table of data. In this case, the independent variable is being called t, the dependent variable is being called x. The t value increases by 10, increases by 5, increases by 35, increases by 15. So the t values are not increasing at fixed increments. And we notice the x values continue to increase, but it looks like we're going to have to do some computation to figure out whether or not the slope between any two points in this table, data points in this table, we need to figure out whether or not this is constant. So let's do a calculation of rise over run. So I'm going to work with the first 2 points in my table. So if I calculate the slope, I get the slope is 45 minus 20. And let me just remind you what slope formula I'm using here. In this case, I'm looking at the change in the x values over the change in the t values. So my slope is 45 minus 20 over 10 minus 0, which is 25 over 10, or 2.5. So when I choose other pairs of points, I want to make sure that I get a slope of 2.5. So I'm going to pull out my calculator to check the other computations of slope. So I know I want to end up with 2.5. And let me see my table of data here. So I'm going to work with the second and third column of data, and I'm going to look at the difference in the x values over the difference in the t values. And when I enter this into my calculator, I need to use parentheses to group the difference in the numerator before I divide it by the difference in the denominator. So I'm going to use open parentheses, 57.5 minus 45, close parentheses, divided by, open parentheses, 15 minus 10, and that equals 2.5. That's what I was hoping for. Let me look now at the third column and the fourth column. I'm going to look at the difference in the x values, 145 minus 57.5, 145 minus 57.5 divided by 50 minus 15. That equals 2.5. One last calculation to check. I want to look at the last two columns in my table. So the difference of 182.5 and 145, close parentheses, divided by, open parentheses, 65 minus 50, that equals 2.5. So I checked the slope between consecutive columns in the table, consecutive points in the table, and I found that each time I got a slope of 2.5. So I can conclude that the data in the table represents a linear relationship, since the slope is constant. And I'm just going to make a note here that I did a calculator check, just to justify that I did the computation. Here we have another table of data. Let's see if we see a pattern in the table of data. Well, my independent variable now is called n. My dependent variable is r. My independent variable is increasing by 2 as I move from one column to the next. My dependent variable r goes up 3, things are looking good, but then it starts going down and going down. Well, there's a very nice pattern here which I can describe, but it doesn't appear to be linear. The dependent value increases and then it decreases. We know that when we have lines, that if we have a positive slope, it is an increasing line, and a negative slope would indicate a decreasing line. Well, if a line has a constant slope, the slope cannot be both positive and negative. So now let's state a conclusion. The data in the table is not linear, since we do not have a constant slope between the points in the table. Let's look at one last example here. So now we are back to x and y, and we want to think about whether or not the data in this table are linear. Well, let's look at the x values. The x values are increasing very nicely by 1 each time. What's happening to the y value? Y value increases by 1, then 2, then 4, then 8. Actually, I see a very nice pattern in the y values. If I look at them closely, I see the y values are doubling. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So there's a very nice pattern in the data in this table, but it's not linear. I have a constant run, but I don't have a constant rise. Let's look at a graph of this data to confirm that it's nonlinear. So I'm going to make some room for graph paper here, and I'm going to set out to graph this data. So I need to pull out my ruler so I can put some axes into my graph. One of the things I notice is that the coordinates of all my ordered pairs are positive, so I want my graph to live predominantly or live entirely in the first quadrant. So I'm going to put my vertical axis to the left of my graph paper and my horizontal axis near the bottom. So I'm going to label my horizontal axis X and my vertical axis Y. Now I need to choose a good scale. Well, my X values are going from 0 to 4. If I choose a scale of 1, everything's going to be kind of crammed very close to the vertical axis. So I think I'll choose a scale of 1/2 instead. On my vertical axis, I need to go from 1 to 16. I think a scale of 1 is going to work for me here. So 2, 4, 6, 8, 10, 12, 14, 16. And now let me plot some points. First point in the table is the point 0, 1. 1, 2, 2, 4, 3, 8, and finally 4, 16. So you can see that these points do not lie on a common line. So this data is definitely not linear. Let me just state that conclusion. So the data in the table is not linear since the points do not lie on a common line. This conclusion is another way of saying that points do not have a common slope. Same idea, just a different way of looking at it. The last thing we're going to do is talk about how to generate these tables of data from a verbal description. So here's a problem. Pappy's fan club purchased a digital recorder to record all the Red Sox games broadcast. The club paid $540 for the recorder, but the value of the recorder has been decreasing by $15 each month. What we'd like to do is create a table that gives the value in dollars of the recorder in terms of the amount of time since its purchase, which we're going to measure in months. So I have here the essential information, which I'm going to use to fill in a table. So I'm just going to choose some months here. I certainly want to know about the value when it was purchased, and I'm just going to let my months increase by 1. And now let's talk about the value. When we purchased it, no time had elapsed since purchase, so the value of the recorder was $540. 1 month later, that value has decreased by $15. So it's now worth only $525. Another month later, the value loses another $15. Another month later, value loses another $15. Yet another month later, value loses yet another $15. If this trend continues, eventually this digital recorder will be worthless. Its value will be 0. But that is if this trend continues. So what we actually used here was slope. The slope, if I looked at this data, I see that the rise is negative $15. The run is 1 month. So the slope in this situation is negative $15 per month. Well, that information was given to us in the original problem. We were told that the value of the recorder has been decreasing by $15 each month. We were given information about slope. One last example. Here we have a mobile phone company with nationwide long distance, and it charges $50 per month, which includes 500 free minutes. But on top of that, they charge 15 cents a minute for each minute of use after 500 minutes. What we're being asked to do in this table is to complete a table, sketch a graph of the situation, and finally discuss the phone charges in terms of slope. So here's the essential information we're going to need to create our table. So our independent quantity here is going to be time. This is the amount of time we're talking on our phone each month, measured in minutes. The dependent quantity is going to be the monthly charges measured in dollars. So let's fill in the table. So I'm going to choose some lengths of time that I might use my phone over the course of the month. So I might not use my phone at all. I might use it for 250 minutes, somewhere between 0 and 500 minutes. Let's look at the charges if I talk just 500 minutes. 501 minutes. Let's see what happens if I talk 1 minute over the 500 minutes included in my charges. 600 minutes and 700 minutes. Now I'm going to use the information given in the verbal description to fill in the monthly charges. Well, the company is going to charge me $50 for the first 500 minutes. So if I don't talk on my phone at all, they're going to charge me $50. If I talk for 250 minutes, they're going to charge me $50. 500 minutes, they're going to charge me $50. Notice there's no change in the monthly charges. But now, if I talk 1 minute over 500 minutes, they're going to charge me an additional 15 cents. So my bill will go up to $50.15. If I talk for 600 minutes, that's 100 minutes over the 500 that I've already been charged for. They're charging me 15 cents per minute, so that will be $15 per 100 minutes. So my charges are going to go up $15 from the 50 they were at 500 minutes. If I talk for 700 minutes, that's an additional $15. So my monthly charges will go up to $80. Let's graph this data and see what it looks like. So I have the data we just computed here in the table. I'm going to set up a graph of this. So again, I'm going to have to pull out my ruler and draw some axes. Again, this data is going to live in the first quadrant. So I'm going to put my horizontal axis down near the bottom of the graph paper, and my vertical axis over here to the left. And now I need labels and scales on my axes. Well, on my horizontal axis, I'm looking at time measured in minutes, and on my vertical axis, I have monthly charges measured in dollars. So my time that I considered was from 0 to 700 minutes, so I think I'm going to use a scale of 50 on my horizontal axis. So there's 100, 200 minutes, 300 minutes, 400 minutes, 500 minutes, 600 minutes, 700 minutes, 800 minutes. On my vertical axis, my charges in my table go up to 80, so I want my vertical axis to go up to 80. So I think I'll use a scale of 5 on the vertical axis. Now let's plot some points. We have 0, 50. We have 250, 50. We have 500, 50. We have 600, 65. And finally, we have 780. So these points certainly do not lie on a common line, but I see two common lines in this graph. From 0 to 500 minutes, I can connect these 3 points using a horizontal line. After that, the last 3 points all lie on a common line, which is increasing. I have what's called a piecewise linear graph. I've got 2 linear pieces. So the first part of my graph is horizontal. This has a slope of 0. So we have a slope of 0. What are the units? Well, the units are going to be dollars per minute. My monthly charges aren't changing from 0 to 500 minutes. The second part of my slope is going to be, well, let's see, we have a rise of $15 over a run of 100 minutes. 15 divided by 100 is 0.15. So my second slope is $0.15 per minute. So what is this telling me about my phone charges? Just what I was given in the verbal description. The slope, M1 equals $0 per minute, means the monthly charges are constant for the first 500 minutes. The second slope, m sub 2 equals $0.15 per minute means the charges increase at a rate of 15 cents or $0.15 per minute after 500 minutes. So what we're seeing here is that if we only had a graph, or if we just had a table of this situation, we would be able to write a verbal description of our monthly phone charges, which is very similar to the verbal description we were given that we started with. So that ends lesson 14. Now we're going to explore slope in more detail in later lessons, but we're going to look at it in the whole in terms of working with linear equations.